In this chapter, we will discuss 4 different organic macromolecules. The first one that we'll discuss is carbohydrates, and this is going to set the tone. A lot of vocabulary is intertwined within all 4, so understanding the first one is going to be most beneficial. On this screen, we have many of the terms that are associated with specifically the carbohydrate. Whenever you see the suffix saccharide in any of these words, really associate that with a carbohydrate. Carbohydrate is the fancy term for sugars. A lot of people often think that they are different in terms of the way that they use it. They say carbs versus sugars. They are one and the same. Here we have 3 categories. This first, all the way on the left here, are called monosaccharides. Mono being 1. Because the smallest part of an organic molecule, or the building block, as you might know it in middle school, is more officially referred to as a monomer. Monomer, the smallest unit of a macromolecule. So it has still that prefix in both. The specific monomer for the carbohydrate is a monosaccharide. There are 3 types. In this video, you'll have to kind of recognize some of the examples. We have glucose, probably the most familiar to you. We have fructose, maybe one also that you are familiar with, and probably the least common that many people know is galactose. The ending is what you associate as a sugar. That's the giveaway that the name of the molecule, if it ends with ose, it's most likely or always going to be a type of sugar. In this case, we'll first have to break down the elements that are present. So the ones that you can see here, within even a glucose, there are hydrogens. So if there's a hydrogen in a glucose, that means that hydrogen is present, as you can see in all of them. So hydrogen is in the chemical formula of all carbohydrates, as is oxygen. All right. And third, we have a carbon here. Technically, every corner, and I'll draw them in, these are your carbons. So if we look at the chemical formula, you can add these all up. There are, I just drew in 5 of them with a total of 6. So monosaccharides, in all 3 versions, actually, they are going to have 6 carbons. You can count up the hydrogens, but what you'll find is that there are 12 hydrogens, followed by 6 oxygens. So the giveaway of a carbohydrate, the word carbo comes from the carbon base to the molecule, and the hydrate comes from the idea that the H to O ratio in a simplified manner is actually a 2 to 1 ratio, which is pretty much what water is. So there is that idea of hydration or hydrate or water. A carbohydrate, these are the 3 elements that are found in every single one of them, with that specific ratio of a 2 to 1 ratio. Technically at the monosaccharide level, it's a 1 to 2 to 1 ratio, but that ratio is going to be going away. But what will happen, the 2 to 1 will always stay. So recognize the hydrogen to oxygen as being your premier way to distinguish it as a carbohydrate. Fructose and galactose have the same chemical formula. And since they have the same chemical formula, but you notice that they are structurally, the 3 of them are unique. You will never have to know by identification which one is which, but the term that gets applied because we have the same chemical formula, but the different structure, that is referred to as an isomer, which a word you might recognize. So the 3 basic monosaccharides, which are all labeled there, something to kind of familiarize yourself with those names. The next level of a carbohydrate is a disaccharide. So we have that saccharide, which means that sugar, and then di as a prefix meaning that's 2. So it's 2 monosaccharides that have chemically joined together. So in this case, we have a glucose and we have a fructose. And when a glucose and fructose chemically combine, they make a new level or a new molecule called sucrose. This is your table sugar. If you are familiar with the scientific name of table sugar, it's just sucrose. Another example of a disaccharide is lactose. You find that in a lot of your milks and things like that, dairy. Some of you might be lactose intolerant. You know someone that is. We'll talk about that means in a future class. Galactose and glucose. So it's a different combination. A disaccharide can be any of the combinations of monosaccharides. Then there would be a third variety called maltose, where maltose would actually be 2 glucose molecules chemically joined. The process by which this occurs is a very, very important process. I'm going to skip ahead. The next slide will show this. It is referred to as dehydration synthesis. Now the word dehydration, if you know dehydrate means to take away water, you do not have water in a system. So what happens before the reaction? We had our individual monosaccharides. We had the C6H12O6. We had our C6H12O6 with a fructose though. Now what will happen are adjoining branches right here with our OH group and our H, they're already been highlighted. What will chemically happen is a bond will break on both of them, and they will chemically join together to form water. So two H's and an O are removed. And because of that, we have some elements over here. We have a carbon, which is not identified. It's just the simple way that they draw it. And over here, we have an oxygen. So what will occur, there is going to be a chemical reaction. That arrow indicates that. Now, this oxygen, which was part of the fructose molecule here on the right, is now chemically going to join with the outer orbital of the carbon, which has an opening. So now there is going to be a bond that forms. So this full molecule now is one connected chemically molecule called sucrose. The chemical formula, you might just want to double C6H12O6, but you have to think about, we lost some stuff in that process. So this is not going to be a C12H24O12 molecule. I get many students that immediately think that's going to happen because they already forget that water was removed. So we didn't lose any carbons. So there is going to just be a doubling of the carbon number. You can count in here. Might be a little harder because of where the carbons that aren't identified from the diagram. But it's C12H22. It would have been H24, but we lost 2 hydrogens in the process of dehydration synthesis. And oxygen-wise, we have only 11 because we lost 1 in the water molecule. So sucrose is C12H22O11. You can see that that ratio is still perfect between the hydrogen and oxygen as a simplified 2 to 1. It's no longer a perfect 1 to 2 to 1 ratio, and that's what I was just talking about a few minutes ago. So recognize carbs with this specific 2 to 1 ratio. So every single time that this occurs, another dehydration synthesis reaction would take place. The bond that forms here, they label it here, it's called a glycosidic linkage. Sometimes I'll just call it a glycosidic bond. So that is a word to recognize, glycosidic. Glyco is a prefix that is many times associated with carbohydrates. In this case, it is the bond that forms. So if I go back here, in a disaccharide, you would only have one glycosidic bond or linkage between 2 monosaccharides. Over here on the right, in a much larger molecule called a polysaccharide, every single connection here would have been a process of dehydration synthesis. So even if I just look at this branch of the polysaccharide, 4 monosaccharides are connected in what I just circled there with 3 glycosidic bonds between them. So that would have made 3 dehydration synthesis reactions occur. So you can look at a polysaccharide and see that its branch is not completely linear. This is glycogen. So glycogen is a much larger carbohydrate. It is the macromolecule example. We have glycogen in our bodies as a mechanism for storing energy. So this, to go from all the way monosaccharides to polysaccharides, is a lot of dehydration synthesis reactions. And we do this as a part of the process of carbohydrates to store energy. When we want to break that molecule down and actually get energy out of it, when that glycogen in your body says, hey, we need the energy, we need to actually break it down into its monosaccharide version. And that process is the reverse of dehydration synthesis. Many students want to immediately say rehydration synthesis. Do not fall for that. This is a term called hydrolysis. These words are going to come up throughout the entire year, so it's best if you really understand it right from the beginning. Hydro, there's that water prefix. Lysis is going to mean to break, and we're going to see that prefix a lot throughout the year as a suffix and prefix, that LYS as well. So hydrolysis is actually going to be the separation of this water molecule. So that water that was coming out with dehydration synthesis, if we want to break sucrose down from a disaccharide down into its individual components, we need to replace the portions that once that glycosidic bond broke, So there is the oxygen. It was at one point connected. There it is up here. That was our glycosidic bond. With hydrolysis, this bond breaks. And so now this oxygen, which has been separated, needs to fill that outer energy level of its electrons. So the hydrogen from within the water will now fill that void. The OH will now go back to where it originally was on glucose. And this is referred to as hydrolysis. We'll talk about what this molecule, it's called an enzyme, but you don't understand proteins yet. So later on, if this video was watched after understanding proteins and enzymes, you would understand its role here. But this process would require the help of protein to do, and that is something which, hopefully in a few videos that will completely make sense. So there's the C12H22O11 with a breakdown now back into its monosaccharides. So they do that process so that when we need energy, we use energy in the form of monosaccharides to go into our mitochondria, which I'm very familiar with, the idea that you understand what a mitochondria is. And we'll talk even more about it in the coming weeks. So that's hydrolysis, and carbohydrates, to finalize things, talking about usage, I just mentioned it a little bit, but it's really about energy. Monosaccharides are for quick energy. So if you have something that is really filled with glucose or sucrose itself, you're going to get a lot of quick energy immediately out of it. Not really good for long-term storage. But then if you have a polysaccharide, that is for more long-term energy. Complex carbs, as they're called, long-term energy. We store ours in the form of glycogen, but another very equivalent molecule, which you are probably very familiar with, is the idea of starch. And so starch is a plant polysaccharide. When we store our energy, we store it in this form. Plants do the same thing, but they don't make glycogen, they make starch. And so when you need energy, that's why we go to a lot of foods that contain starch, such as pasta and potatoes and things like that, where we can get some long-term storage out of. So we would just break starch down in the same process. We break all these bonds that are between the monosaccharides, and when we do, all these monosaccharides can enter the mitochondria and we can get their energy out of them. But you can see how long it takes me to do this. This is why it's more long-term, because you'd have to go in and start breaking all those bonds. Whereas quick-term, I just have one bond to break, and we would be back down to monosaccharides, which is what we can immediately get energy out of. So that's carbs. We'll do a video for each of these, but this is a really starting point for the chapter, and understanding dehydration, synthesis, and hydrolysis will be a very important concept for the coming videos.